I'm going to start just by introducing myself a bit. Maybe what I do is not so familiar to all of you. So I'll tell you something about that. Then I'm going to talk about some early collaborations we've had with several people, Fraser Stoddard, Shufeng Guo. And then most of my talk will be about our study of molecular gears, our computational work in collaboration with Miguel Garcia-Garibay, my colleague here at UCLA. So first with my group. So this is a picture from pre-pandemic era. We're not quite as large now and we're distributed in various places, but we still have a lot of different people doing computations and all kinds of things. And the programs we use are pretty standard. We're doing quantum mechanics and molecular dynamics. And we use Gaussian. Popel's program started in the 70s that now Mike Fisher's the CEO of the Gaussian Corporation that distributes this. Orca is a NASA's wave function program that we've used frequently recently. We do our molecular dynamics with Gaussian or with Progdyne, and Dan Singleton, Texas A&M, wrote this for studying reactions, and I'll show you a few examples of use of that. We do protein dynamics and solid state dynamics, such as I'll describe for you, but with Amber. Dave Cases, they have a big consortium that runs that. We do a lot of conformer searches with various programs, and the computers we use are at UCLA. We have a big shared cluster. We also have a GPU cluster in my group for protein dynamics. And then we rely heavily on the NSF Exceed, changing to Access soon. The main computers we're using at the moment are at San Diego and at Pittsburgh. So these are the list of various organic problems that we're very interested in. My general interest is in exploration of organic reaction mechanisms with quantum mechanics and molecular dynamics. We study pericyclic reactions. I'll show you an example of that if you're not familiar with what those are. Organocatalysis, photochemistry, transition metal catalysis, radical reactions. We're pretty heavily involved in enzyme catalysis and design of new enzymes. And we have some collaborations with our colleagues in engineering on organophotovoltaics. So I'm going to give you an example of exploration of organic reaction mechanism, just to give you a flavor of what we usually do. And it has to do with the pericyclic reaction. I also mentioned briefly some of the things we do on enzyme catalysis. So this is a organic reaction between two compounds shown at the left. And this is called a heptafulvene and a fulvene. And they react to give three products shown at the right here. This has been studied experimentally last century by my former grad student, Siwai Liu, who's a professor in Taiwan. And then my group just recently, a couple of years ago, studied this computationally. So it's an example of a pericyclic reaction. A pericyclic reaction is one in which all the bonds are formed in a single step on a ring. That's the cyclic part. And beginning with the work of Caramella and then our work, we've found a number of these reactions which involve fairly complicated looking transition states. So in this transition state, which I'll blow up here so you can see it better, there's one relatively short bond. This bond between the green atoms is about 2 angstroms, but there are 3 others that are about 3 angstroms. And we call this bond that's going to be formed between 1 and 2 the primary orbital interaction, because that's present in all 3 of these products. But the other 3, it depends on which trajectory is followed, which of the products is favored. So just for example, if this red bond is formed between 3 and 4, then the 1, 2, and 3, 4 bonds are formed in this product. And it's called 6 + 4. That has to do with the number of electrons on the 2 systems that are involved in bonding changes. So we study those things quantum mechanically, and then with molecular dynamics also. I'll just give you one example of that. So here's one trajectory, and it's a trajectory that's going to lead to this compound labeled 3B. So we do quasi-classical dynamics starting from the transition state and run in both directions, and then I put those together into a movie. And we're at the transition state about here, and then this bond is formed, and then soon thereafter, the second bond is formed, and that leads to this product. And it looks like this has happened sequentially. However, the gap between the time at which the two bonds are formed is only 41 femtoseconds. So 41 times 10 to the minus 15 seconds. So this is on the order of a CC vibration, is a little faster than that. But we call this concerted, dynamically concerted, because the two bonds are formed within the time scale of a normal vibration. So that gives you an idea about the kind of things we do on mechanism. We look at details of how reactions are formed and multi-step mechanisms, but also the timing of bond formation. And here I have a little advertisement of a paper published Natural Product Reports a couple of years ago, where we describe a class of enzymes we call PERICYCLASES. So these are enzymes that catalyze pericyclic reactions like Diels-Alder reactions, co-prearrangements, things of that order. I won't talk about that in detail, but just to alert you that this is one of the subjects we're interested in and trying to understand how enzymes are capable of accelerating the kind of reaction I just showed you on the previous slides. But let's turn to the favorite subject of this group, and that is molecular machines. And it's easy to find a lot of nice images on the web for molecular machines. There are a couple here in motion here, which are the kind of things I'm going to be talking about in the rest of my lecture. So first, I'm going to start just with a couple of recaps of early collaborations in this field. It was really Fraser Stoddard who brought me into the field of nanoscience or nanochemistry. And Fraser was my colleague at UCLA between 2007 and 2017. This is a article that we published together with Ximin Ho, who at that time was in our engineering department. And it has to do with one of Fraser's shuttle molecules. This on the left is something that upon oxidation of the green unit will change its conformation. The blue box, as he calls it, moves to a different location. And in this particular experiment and our computational simulation of it, this molecule represented in this graphical display was attached to a gold surface at the bottom, and also to the tip of an STM at this top gold position. And then it was possible to measure the forces that are induced by this kind of change in the shuttle geometry. This is Fraser. He's now at Northwestern. This is probably when he was toasting for the Nobel Prize in 2017. Okay, we also do work on what might be considered molecular machines, but they're certainly single molecule chemical reactions with this gentleman who's Professor Xue-Feng Guo, who's a professor at Peking University. And he's developed a way to sequester molecules between the tips. These are graphene tips. So he is attaching this molecule, and then attached to it is in red here is something called a Malay imide. It's a reactive molecule in a cycloaddition. That's a pericyclic reaction with cyclopentadiene. So this little picture is cyclopentadiene. It can react, they form a complex and then form a adduct. And he's able to follow the formation of intermediates like this complex and the final product by measuring conductance through these electrodes. And he also is able to apply electric fields and see how that influences the reaction. In this case, with a high enough electric field, it's possible to change the mechanism and get a zwitterion here. Of course, this is highly stabilized by an electric field that then leads to the same product. And of course, from these traces, it's not really possible to get any structural information. He gets timing of and some information about energetics, but we have to do calculations in order to elaborate what structures correspond to the various intermediates that he detects. Okay, so now I'll turn to the main subject, which is gearing. And this is another picture of Miguel Garcia-Garibay. He's in the chemistry department. He's also the dean of physical sciences at UCLA. And these are the two grad students, or at least they were grad students at the time, who worked on were the main drivers of what I'll be talking about. Eva Liapuaniti was a joint member of the Garcia-Garibay and Houk groups. And she's now at IBM in the quantum computer project. And on the right is Sung Yang. And Sung Yang was a grad student in my group who did computations on Garcia-Garibay's work. He's now a scientist at Merck doing research on drug design. So Garcia-Garibay is interested in building molecular machines that resemble real devices. So, for example, gyroscopes, one of his favorites, molecular compasses. So the idea here is to have substituents on this rotor that could allow this to be oriented in a magnetic field like a compass is. And on the right, molecular gears. Here's an example of two tryptycenes intermesh that are gearing. Garcia-Garibay has been very interested in the variation in molecular order and molecular motion in different kinds of materials. So, for example, glasses have both low molecular order and low molecular motion. Crystals, on the other hand, have very high molecular order, but also low molecular motion in general. I'll show you some exceptions. And then what's graphed here are various kinds of materials going down to liquids, which have considerable molecular motion, but very little order. And Garcia-Garibay is particularly interested in what he has named amphidynamic crystals. This means multi-dynamics. That's because they have structural rigidity, but they have moving parts, as I'll show you in a moment. So here are a few examples. A moth that might have a tryptycene that would be rotating rapidly, although the overall moth structure, of course, is quite rigid. And he has also studied crystals of this kind. Here's one that has, of course, a rigid structure, but has moving parts. So our group is doing the computational part. We do various things, molecular dynamics, DFT calculations, metadynamics, Monte Carlo sampling. And the Garcia-Garibay group is doing what's on the right here. They are started with solid state materials, but now are involved in characterizing a variety of materials, studying molecular motions of dynamics by variable temperature, NMR primarily, and then, of course, involved in the synthesis of these compounds. So here are the kind of molecules I'm going to be describing. I'll say a little bit more about this later, but this is an example of the Spur gear. Two tryptycenes, that's what these triphenyl bicyclid two tetrienes are called. This is a tryptycene, this is another tryptycene. And as you might imagine, they can rotate in opposite directions and do have gearing motions. So let me say a little bit more about this idea. Let's see if I can do that change. When we have gearing motion, then in a spur gear of this kind, we call that a disrotation. That is, the two have to rotate in opposite directions in order to establish gearing. So here's an example of that happening. But on the other hand, especially with these this three-tooth gear, there's the possibility for slipping also. That's what's going on here. These are both rotating in the same direction, called this conrotation. That's really undesirable in a machine. You don't want it to be able to slip. You want it to always gear in the manner shown at the top here. Now, what I'm showing you here is idealized arrangement. In general, for molecular gears in this stage, they involve Brownian motion, not this kind of continuous motion in one direction. Of course, people like Ben Feringa have determined a way using photochemistry to drive motion in one direction. But in general, what I'll be showing you doesn't have that built in yet. So the observation is of Brownian motion instead. So we use a measure of gearing fidelity as the ratio of gearing to slippage, or gearing to slipping, as listed here. So let's say a little bit more about specific molecular gears. So J. Siegel was a pioneer in this field. J. Siegel started at San Diego, then moved to Switzerland, and then he moved to China in Tianjin University, and then he moved briefly to Vietnam, and now he's back in Switzerland. But back in his San Diego days, he synthesized this molecule shown at the upper left. And this molecule has two tryptycenes shown here. And in this picture on the right is just a view looking at the from this direction towards those gears. Looking from this direction towards this, that's what you see here. And then this is a superstructure. There are two axles here that hold the tryptycenes. And this is a picture of the transition state for gearing. This is when these two things are rotating in opposite directions. The right one counterclockwise and this one clockwise would give this transition state. This is the highest energy point between two ground states. But the slippage can also occur. And in fact, Siegel was able to use NMR and to determine that most of the time slippage occurs in this, with this particular gear. So Garcia-Garibay's group, in particular, these three gentlemen at the bottom, Xin Zhang, Marcus Jelen, and Mingyu Jin, the two on the left and right are gone now, but Marcus is just finishing his PhD. They devised this macrocyclic version of the Siegel gear. This has the other ends hooked together for reasons I'll show you in a minute. And they were unable to synthesize the molecule with just putting another one of these on the other side. Instead, they came up with a rather clever idea of having an acetylene that's attached to a gold, and then in turn is coordinated to a phosphine on this diphosphine molecule. So it has the benefit of locking in the other end of the molecular gears. So this is a picture of the ground state. Now we're looking from the bottom. And here's a picture of the what the transition state for the gearing looks like. Now here's a picture again of disrotation and conrotation occurring, the gearing and slippage. And it turns out that in the molecules that have been synthesized by the Garcia-Garibay group, sometimes gearing is faster than NMR timescale. That is that even going to rather low temperature in the NMR, still the rotation is too fast to freeze out. So one can't really measure the barriers for rotation or in fact, the speed of rotation, except that it is very fast. But we, of course, can use computational modeling to model that. And I'm going to be showing you a few graphs that have dihedral angles on them. And just for definition here, I've shown 4 atoms that define the dihedral angle for the rotation of the left-hand tryptycene, and 4 more atoms that define the dihedral angle for the rotation of the right-hand tryptycene. Okay, so here's Siegel's half-open gear on the left. As I said, it's primarily slippage, so the gearing fidelity is very low. But on the right, it's found that the gearing fidelity is very high, and I'll show you that more specifically. In the upper right here is shown a picture from one of Siegel's papers in which he calculated the distance required for the optimum ground state arrangement. This is just having 2 tryptycenes nestled up against each other like this. The transition state for gearing, which actually requires the 2 axles to be 8 angstroms apart instead of what it prefers in the ground state. The transition state for slippage can occur at a reasonably small distance. So there's a problem here that with this 3-pronged gear, that a short distance will favor slippage, and one has to enforce a larger distance in order to get gearing. And that's really what was achieved by having this holding apart the tryptycenes. And in fact, here's a way that shows that. We do molecular dynamics on this. We're using amber in this case. It's a force field. And we're doing it just on this molecule. We've done it for materials also, but I'm just going to be talking about this molecule that has gearing due to these two tryptycenes. And this so-called probability density is just, we do dynamics for, let's say, a few picoseconds, and then we will take snapshots of the geometries at various points in the dynamics. And this is a graph of that. So in the case of the green, this is the Siegel molecule. You'll see that the average distance is around 7.5 angstroms. So it's pretty good for the slippage. In fact, that's probably why the slippage occurs. But the Garcia-Garibay molecule has an average distance around the correct distance for gearing, around 8.1 angstroms. So let's look into the dynamics in more detail. So what I've plotted here is a dynamic simulation. These are microseconds from 0 to 1 microsecond for the gearing of the Garcia-Garibay molecule. And these are the two dihedral angles I was referring to before. And I've shown with arrows where gearing events happen. So that's where the two are rotating in opposite directions. So this blue one, let's consider that the left-hand one, is now going to a more negative dihedral angle. At the same time, the red one, the right-hand tryptycene, is going to a more positive dihedral angle. And they're always moving in opposite directions. So that's the signature of gearing. And you'll see over this 1 microsecond, at least at low temperature, 207 K, that's all that's happening. And here's a different way of looking at it. These are the plot of the two dihedral angles in the X and Y axes. And these are various snapshots taken, just showing what the structure is at various times. And moving in this direction along the diagonal is the direction of gearing. And you'll see that very rarely there's a molecule here that must have undergone a slippage to get over here. But most of the time, we just have molecules clustered along this diagonal, which corresponds to the gearing motion. And the various globs here are due to the different ground state minima, where the dihedral angles are such that they're like what I showed you before for ground state. Okay, so this is the low temperature. If we raise the temperature 247 K and do dynamics again over 1 microsecond, we do occasionally see slippage. Not too often. Most of the time, this is gearing again. But here's an example where the dihedral angle of both the red and the green, as listed here, are changing in a negative direction. That's a conrotation, a slippage. And here's another example. Here also is the other way to show this, showing that, well, indeed, there have been significant leakages away. If we start in this region, go this way for gearing, that we have significant buildup of that could only happen by slippage. And at 300K, well, you can't see much from this. It needs to be spread out for you to be able to see it. But you can see from this diagram that of course, there is significant gearing, but there must have been slippage to get these population along these minima. So we studied this in another way with metadynamics, just a brief mention about that. Metadynamics is done by, it's based on populations from molecular dynamics. At the bottom here is shown the idea that this is a method from Michele Parnello, where one does molecular dynamics, and let's suppose we start in this region of a potential surface that has multiple minima. Suppose we start in this region. If we do molecular dynamics, the molecule will just wiggle around in this region for a long time. And that's an indication that that's a relatively low free energy. We then need to add potentials that force the molecule out of that region. So here's just pictorially, these blue lines are the various potentials. And eventually, if you add enough of those, that then the molecule will slip over into a lower energy nearby minimum. And if you do that over the whole surface, you can reconstruct the free energy of the surface. And that's what this picture is. So this is a color-coded energy. It's looking for essentially free energy for the different points on this surface that are represented by the two dihedral angles. So the dark blue are the minima that I described earlier. The moving in this direction, they're relatively light green color, meaning it's relatively low energy for gearing in this direction. But the color here should be a brighter yellow, indicating a higher energy for the slippage in this direction. Okay, so that's one kind of study. Here's another one. It was actually based on work of Shinoya and his group in Tokyo. And they created a molecule that, instead of being a Spur gear, like I've talked about so far, is a bevel gear, in which the two gears are perpendicular. The axials of the two gears are perpendicular to each other. And this is a kind of a complicated molecule. It's a dirhodium complex. These are very common molecules that are held together by 4 acetates. So it might be a little difficult to see in the picture. Let's look at the left-hand one. So these 2 oxygens are part of a carboxylate, and 1 oxygen is coordinated to each rhodium. And then the other atom attached to this carbon is attached to the tryptycene. So here's a tryptycene. And there are 4 such units in this molecule. They're each interacting in a bevel gear way, but there are really 4 units now of these tryptycenes that are involved. Here's a cartoon picture of the same thing. And one other thing that's important in this, what we've studied, is the L here. L is the ligand, and those ligands, I'll show you the structures in a moment. 3 different ligands cause the rate of rotation of these, measured by dynamic NMR, to be different. So with the ether, it's a relatively fast rotation. With some of these others, a slower rotation occurs at 260 K. Here's another view. And now here's a picture of the dynamics of this molecule 1. So this is now this bevel gear undergoing Brownian motion. So it's a little hard to see. This is a complicated molecule. It's sort of hard to see that rotation of the tryptycenes are actually occurring. And the fact that it's always geared. There's no slippage here. These are integrated in such a way that slippage is not really possible. And so only gearing is observed. This particular structure has 2 dimethylamino as ligands at the bottom and the top. And this is one of those that undergoes rather rapid dynamic motion. So on the bottom right here are shown the 6 ligands, and these are cartoons, but ethylpyridine, methylpyridine, ether. This is pyridine itself, dimethylaminopyridine, and this is a pyridine with a methyl ester attached at the 4 position. So here on the left is shown a blow up of part of this molecule, showing the bevel gear interaction of 2 tryptycenes. Here's again that dynamic simulation. And shown at the right are 6 different complexes with different ligands at the top and the bottom. And also are given the enthalpy of rotation measured by Shinoya's group by variable temperature NMR. So with the ethylpyridine, this is the highest barrier, 18 kilocalories. With methyl, it goes down. With just a simple diethyl ether, it's even lower. And these 3 were undergoing rotation too fast to be measured by NMR. So we explored this computationally. Shinoya suggested that the barrier was being influenced by the ligand by steric effects. And we've shown that in a more quantitative way. So first of all, we did quantum mechanics. The numbers in red are the numbers I just mentioned that were measured by Shinoya. The numbers in blue are those calculated in our group. And this work was done, I forgot to mention, was done not only by Ava, but by Jacob Sanders, who's a postdoc in my group now. So we don't get the number right on. The way we do this is a traditional calculation of quantum of transition states of quantum mechanics. Namely, we optimize the ground state, and then we locate the transition state, which is the saddle point for rotation of the 4 tryptycenes, and calculate the difference in activation enthalpy. So we underestimate this. Is done with density functional theory, P3O at PD3. it's uniformly low, but we get the trend very well. So this is the decreasing barriers measured experimentally in red, and these are the decreasing barriers computed in blue. And we're able to compute that the barriers that they were unable to measure are indeed very low. Let's say if we have the same roughly 3 or 4 kilocalorie error, but they're probably on the order of 8 to 7 kilocalories per mole rotational barrier. So very fast rotation is occurring. And the origin of that we can probe computationally. And we did that using something that's kind of a popular modern measure of steric effects, namely the percent buried volume. This was developed originally to study various ligands on metal complexes. It's the percentage of volume of a sphere that's occupied by the ligand. The sphere is arbitrary. We use about 3 angstrom measurement. And these are the buried volumes as the x-axis here for the different ligands that I mentioned. And 3 of those are very similar to each other. And those have essentially the same barrier, calculated to be around 5 kilocalories per mole. But as the buried volume increases, the barrier rotation increases as well. So that's good quantitative verification of the surmise from the Cianoia group. So what I've had the opportunity to tell you about are a few of our studies with the Garcia-Garibay group of gearing. I talked first about this macrocyclic gear, and then about how varying ligands can alter the rate of rotation in these molecules. So today I've described our use of computations to explain phenomena discovered previously by experimentalists. So this is just rationalizing. So maybe I shouldn't be talking to the Foresight Institute, but the Hindsight Institute. It's a lot easier, of course, to rationalize things than it is to predict them. And of course, the Foresight Institute is not geared for rationalization. It's more visionary for predicting things. And of course, it's inspired by Feynman. This is the famous blackboard left when Feynman passed away. And in the upper left corners is what I cannot create, I do not understand. And indeed, the eventual goal is to try to create things based on our understanding. So the plans to create, this is really Garcia-Garibay's vision, but we're involved with it computationally, is to incorporate molecular rotors into things like metal organic frameworks, crystals, and et cetera, to create novel materials. The eventual idea is to have rotors undergoing correlated motion due to dipolar interactions, and also that have collective responses to externally applied stimuli, such as magnetic fields or electric fields. And the idea eventually would be to use these for visual displays, sensors, or in the field of molecular machines to activate molecular machines such as the gyroscopes, motors, levers, and so forth, gear involving things using magnetic or electric fields. Now, what I talked about today didn't really have that possibility because the molecules don't really have, weren't polar, that were undergoing rotation. But Garcia-Garibay is making those molecules and interested in studying them. And we're interested in studying them also with computation. So let me just conclude by thanking, of course, Miguel Garcia-Garibay, my active collaborator. The people who were involved in this work, Ava, Song, and Jacob, and Marcus was the experimentalist from the Garcia group working on this as well. So thank you very much. That's it. I'll be glad to answer any questions.
Yeah, if you want to, thank you so much, Ken. That was great. If people want to just like raise their hands to use a little like raise hand button to do questions or drop them in the chat. Either way is great. So anybody? So if I could, oh, Aaron, go ahead.
Yeah, I thought I was only caught the later part of that presentation, but that was amazing because the gearing systems. So at that scale, how well do the gears work? Because from what I understand, for biological systems, when they operate they tend to use proteins. And I assume maybe that's due to just the complete the limitations of biological systems. But is there anything like problematic with having gears at that extreme small scale in terms of their operation?
Of course, it's quite a challenge to build in the kind of gearing that nature uses. For example, an ATP synthase, very famous when using protein gradients or proton gradients to drive motion in one direction and then to be involved in synthesis. Of course, what I'm talking about is much simpler than that. We're just looking at very simple motions. And one kind of simple challenge in having gearing with high fidelity, that is to not have slippage, as I described in the beginning, is that we don't really have in these molecules enough teeth on the gears to really ensure gearing. So there aren't that many molecules. You can't have fourfold symmetry. It's kind of difficult to have fivefold symmetry, but you can build such molecules that would have more gearing fidelity. But of course, what we're just studying here is motion without any real purpose. It's just random Brownian motion. And of course, what one would like to do is to build things that have, for example, polar groups that can set up an electric field that could be modified by having an external electric field drive motion, for example. Or you could do more elaborate things like Feringa does, such as do photochemistry that forces things to move in one direction.
Thanks. Yeah, that was exactly what I was thinking about, was ATP synthase. So
Yeah.
very cool.
Thank you.
So one question I have is I just sort of thinking about the broader system, right? Like the whole point of gears in real life is to like transfer energy along a shaft to do something. And I'm just have people like I guess like where do you what do you see as like the sort of like minimum viable system that these gears could be integrated into, and what would we need to do to make that happen?
Well, I think the minimal might be to have something like, as I was alluding to, and which Garcia-Garibay is trying to make, which is, suppose you had a couple of cyano groups on one part of that Triptycene. Then you'd have a local electric field for the rotor, and by having an oscillating external field, you might be able to cause rotation. And what you do with that, I guess I haven't really thought too much about that. I've just been involved in trying to understand how these things that various experimentalists have used, how they work. But one could, well, I guess, the silly thing that people have done, of course, in the nano cars, you could actually drive a nano car in a specific direction if you could control the direction of motion of its wheels. And of course, nature doesn't do that, but it does do things like an actin and so forth, where it has ways to move things along other proteins. So that's just an idea, but it's not particularly useful, but just an idea about how the direction this might go.
Yeah, no, I'm actually less interested in useful and more interested in just like how does it then become a bigger thing. So that's a great answer. Thank you. Yeah. Tad, do you want to go ahead?
Oh yeah, hi. This is Tad Houk. I really enjoyed your presentation, and what I was wondering is, for the collective motion that you mentioned, do you see if there's a path of a way to place many sort of interacting gears in a material and maintain the collective motion for all of them, especially with the randomization that you mentioned from Brownian motion, which would seem to kind of prevent, getting long-range correlated behavior from over reasonable distances. Have any thoughts on that?
Garcia-Garibay is making ones that have multiple tryptycenes arranged in a three-dimensional. Actually, it's a two-dimensional array, and of course can observe in the solid state the motion of these units, but hasn't yet been able to achieve this kind of collective motion. again, it's going to be involve having some asymmetry in each rotor so that you can somehow enforce enforce motion in one direction rather than just Brownian.
Do you think that might involve then these external fields that you mentioned?
Right.
As a sort of a way to sort of enforce over, I guess, a larger scale.
That's correct. Yeah.
Okay, that makes sense. Thank you.
So there's something in the chat here.
Yeah. Do you want to read that question from Stephen?
Yeah. So Stefan says, do you have a feel for the energetic cost of correlating the motion, i.e., if you were to drive one rotor directionally, how much energy would be lost transferring that directional motion to the next gear? That's a good question, and I must admit I haven't thought about that. Yeah, so this is kind of a friction question. Of course, when we do calculations, when we go from one minimum through a maximum to a second minimum, and the second minimum is essentially degenerate with the first, then of course their energies are the same. So we're not really considering friction and loss of energy, but of course one does expect that in any if you set things rotating in one direction, that they won't necessarily keep going forever because of friction, at least on a macroscopic scale. On a microscopic scale, yeah. Okay, so he says more. It's more about entropy than friction. Yeah. Yeah. So the entropy is sort of favoring random motion, like in Brownian motion. I think you probably know more about this than I do, and you can perhaps answer your question better than I can. Yeah, you're right. This is an entropy issue. The potential energy doesn't ever change when you do these rotations. It's the same before and after.
Anybody else? Questions? Are there any questions we should have asked you that people are not? If you were to play devil's advocate against your own work, what would you ask yourself?
Well, I guess one I often get asked about how precise or how accurate are these calculations, and of course, I gave you one example where we calculated the barriers, and we think we have a beautiful understanding, and we get the trend of activation barriers right, but we're off by a couple of kilocalories on the barrier. So this is always a system a problem, especially with very large systems, about how accurate the results are. But so in other words, doing quantitative calculations and predictions are going to be very difficult, but we think we are able to get quite a bit of insight into the details of things, even if it's not exactly accurate. Alex, you have a question?
Yeah, hi Ken. I really enjoyed that. So I did my PhD with Steve Loeb, so I was doing kind of Rotors in Ligand frameworks. But
Yeah.
Stefan's brought up a really good point that I keep thinking about. So imagine you have a series of gears, rotors all in a long line, and then you have one motor. So the energy is going to be different if your motor is just moving one gear versus two gears in a long row. So if you scale that down to something like a Feringa motor, so let's say you've got a Feringa motor and every time it turns, it hits the gear next to it, and then that gear hits another gear and hits another gear. You can only put in so much energy into that Feringa motor. I mean, how long is it going to be before essentially your engine seizes? So I've never really thought about that energy transfer between the motor to the gears. It's not going to be 100% efficient.
I haven't thought about that either. So I think that's a really a very interesting point, and I have to think about how to explore that. That's really a great thing to think about.
So I guess the whole goal of this whole molecular machines is some kind of signal propagation. You have a very small signal, and that's going to be multiplied, so on and so forth, until you get some good output. Maybe on a mole of material, who knows? But yeah, if your efficiency is terrible between, how would you even do that?
Right.
I'm questioning everything I've ever thought about molecular machines now.
Yeah.
Thanks, Stefan. Great.
Yeah. These are excellent points, and something I think about. I'll talk with, I think Miguel may have thought about this kind of thing, but I'll discuss with him what he thinks about that too.
All right. Well, if there are no other questions, going once, going twice, then, well, thank you very much, Ken, for joining us. This was really, really interesting. And thank you everybody for participating.
Okay. Thanks for your questions. Thanks. Really thought provoking. I'll think about them. Thank you very much.